Good afternoon. Hope you can hear my voice. If not, let me know so that I can increase my voice. Okay? Yeah, start.
This one could be clear.
Yeah. Yeah. Thank you very much for joining all, and then happy to see you guys. Probably like we'll be having the fire and gas mapping system now. The presentation. The main importance of the fire and gas system in oil and gas industry is now growing. So we need to see that how effectively the fire and gas systems are utilized to reduce the risk. Okay. So in olden days, the fire and gas system is basically on the experience. Like we say, it is prescriptive based. That means based on the people understanding the detectors will be considered in a hazardous plant. Okay, but the detectors considered in the process plant, it is not understood well that whether the detector is over-specified or under-specified. Okay, so that the required detector and its performance is not evaluated in proper way in the prescriptive based. Therefore, there is a standard which is nowadays it is a kind of very important and it's growing in the oil and gas industries due to various limitations. There is a standard like ISA TR.00.07 that talks about that evaluation of or guidance on flammable gas, toxic gas, fire detector in the process industries. Okay, this presentation is mostly talks about that how to ensure that detectors' performance are effectively verified in line with TR 84.0.07 standard. So now, what is the role of fire and gas detection system in process plant? The detectors itself will detect any accidental leak from process plant, and the detector itself will not reduce the risk. The detector need to have an interface with some measures. The interface means whether the detector can give alarm to a human or maybe operator to alert and take action. So that is called interface. Now next interface is like the detectors can be interfaced with your emergency systems. The emergency systems are like emergency shutdown valves, blowdown valves, and deluge system. So that if there is any accidental hazardous chemical release in the process plant, that will be properly interfaced and that action will be taken to reduce the risk by reducing the consequences. Now we are coming to the objective of the fire and gas mapping study. The main objective of fire and gas mapping study is to detect any accidental releases in a hazardous plant and alert the operational and operator, field operator or maybe the panel operator and take necessary action so that the consequences and risk will be reduced in a plant. And the systems involved in fire and gas system, or maybe in short we say is FGS. Okay, FGS means it's a fire and gas system. So it has the main three systems, subsystems we can say. One is detection system. Detection system means like what type of detectors need to be installed in a process plant. So type of detectors comes that whether it is flammable gas detector, fire detector, or it's a toxic gas detector. So even in the flammable gas, we have the typical hydrocarbon as well as you have the hydrogen like that. So you have to look for the type of detection system or detector required in a process plant. So that is a one important system. After that, we have to alert the operator. So alert system is like once a detector detects any accidental leak, that that information should pass on to the relevant person. The relevant person may be the operator sitting in the control room or the field operator. Okay. Also, we can have interface with your emergency shutdown system so that we can take automatic actions. So automatic activation of your deluge system, activation of your emergency shutdown system, blowdown system. So the main three components in the FGS system is like your detectors, alert the people, and then we have a initiating action. Now we are coming to the concept of designing FGS system. So as we say, like the ISA standard talks more of like performance-based design. That means it is including that the risk concept. That means the risk reduction using FGS system is based on the risk-based performance, or we can say performance-based system. So you can, we can see that in the typical hazard and risk analysis, it is to identify the loss or containment events due to process deviation from the normal operation. Whereas in the FGS function, specified is not to actually prevent the loss or containment, because the loss or containment will happen, but to reduce the consequences due to any accidental leak or loss or containment. So the successful FGS function prevents an already bad situation from getting worse. So that is the main purpose of like FGS system. We cannot, FGS fire and gas detectors will not prevent the loss of containment. However, it will reduce the consequence impact. So this is a typical or simple layer of protection is normally available in any process plant. It is starting from the plant design as per standards and the processes. We have the BPCS, that is basic process control system. Where some people, they say it is a DCS system or maybe basic process control system. The next layer of protection is your prevention system with respect to safety instrumented systems. Okay, that is called safety integrity level or safety instrumented system. The next level is mitigation. Under the mitigation, fire and gas system will come under the mitigation. Last layer of protection is emergency response. So you can see in the layer of protection, your FGS system is not preventing the loss of containment. After the loss of containment happens, if there is a potential for any fire, explosion, or any toxic impact, that is going to reduce by FGS system. So it is a kind of mitigative barriers, we can see, or mitigative safeguard. Now, this slide talk about that more of how to develop the process of designing any fire and gas system. This is detailed in line with the ISA standard. It is not something developed by ourselves. It is detailed everything in the ISA standard. No need to remember or something like that by heart this. Just to understand that the broad spectrum is like, first I didn't do the fire and gas hazard assessment. That is the broader way of classification, the first step. The second step is define the requirement. Third one is performance verification. The fourth one is check whether this risk is reduced or not. So we can classify this, your need for FNG system as a four types. Under the fire and gas hazard system, that is actually in the previous lecture, it's already defined how to perform the consequence and the risk analysis. That approach, everything is similar to this, like identify the hazardous areas and evaluate the consequences due to any accidental leak. I'll look for what is the frequency or likelihood of that event is going to happen, and accordingly you determine what is the risk in your plant. Okay, this is more of in that way. Now coming back to the next category is requirement specification. So based on the risk in your plant, you have to develop the specification for FGS system. The specification is depending on your previous experience and also some of the PHA studies you can utilize to develop that. Now the third step is like you can say that verify the detectors, whether the detectors considered as per your qualitative basis or maybe based on the previous experience, whether it's adequate or not. So that is part of the verification. Under the verification only, we will be like doing the fire and gas mapping study and detector quantity, locations, and etc. Now we will be like going in detail about that each and every step. The first step is like you identify the areas of concern. The areas of concern is normally the important study or document you can get is in the PHA report. Okay, the PHA is one of the important documents. Talks about that what are the areas which has the potential for fire, explosion, and toxic impacts. Identify those areas, and also you can look for the quantitative risk assessment studies. Hazard and risk scenarios. Hazard and risk scenarios, again, depends on the type of equipment in the process areas. What is the material being handled by the each and every equipment, and what its conditions, whether it is a gas phase or liquid phase or two phase, and whether it is in above auto ignition temperature. So that kind of conditions will be taken into consideration. Also, we have the other factors will be considered congestion. Congestion is something like that very, very important in the FGS system design. Analyze the consequences. The consequences can be analyzed in a qualitative way as well as in a quantitative way. The quantitative way of analyzing the risk is consequences using the past software is one of the software where we can develop or quantify the consequences due to any accidental leak. And also, we have the another software that is computational fluid dynamic tool. That is, we can use either KFX or FLAX software to determine the consequences. The only difference between the FAST and the CFD tool is like, in the FAST, probably that physical obstructions will not be taken into account, whereas in the CFD tool, the physical obstructions also taken into account while evaluating the consequences. The hazard frequency is the best information to determine the frequency analysis is to use the statistical data. The statistical data will be easily available in the IOGP data bank. Okay, so each and every equipment with the type of equipment with the various leak stages is available. That information can be utilized to determine what is the failure frequency of any fire or explosion event in a particular process plant. Once you have the hazard assessment, you can check what is the unmitigated risk. So unmitigated risk is the best way of determining unmitigated risk is assume that your fire and gas system is not available. So in absence of fire and gas system, check that what is the unmitigated risk in your process plant. And if that unmitigated risk is fall under acceptable region, probably the need for fire and gas detectors in your plant may not be required, but it's purely depending on the owner's need or maybe owner's requirement. If the unmitigated risk is not in acceptable range, then it is a mandatory or a requirement to go for fire and gas detection system to reduce the risk in our process plant. So once you identify the need for fire and gas system, now we have to define the performance of the fire and gas system. Performance means how much of risk need to be reduced by the detectors. So that performance will be determined by this step, like the performance targets define the ability of an FGS function to detect, alarm, and take necessary action. So that is the performance target of any fire and gas detection system. In concept, a higher hazard installation should require higher level of performance, while a lower hazard installation should allow lower level of performance. Say, for example, you have a very high pressure process gas with like example, take hydrogen. The hydrogen will have a very serious consequences compared to any normal typical hydrocarbon. So the hydrogen handling facility or equipment must have higher level of performance, like to reduce the risk compared to any hydrocarbon handling system. So that is evaluate the performance required for the FGS system in your process plant. And depending on the PHA study or maybe the owner's requirement, the performance based FGS performance of that any FGS can be evaluated in two ways. One is semi-quantitative method and quantitative method. The quantitative method is same as your quantitative risk analysis. Therefore, the quantitative method is not detailed here. We will only like talking about semi-quantitative method. So semi-quantitative method is defined are detailed in the ISA standard. So the same thing is I have reproduced in this slide to evaluate the performance target for any hydrocarbon or flammable hazardous equipment in semi-quantitative method. Under the semi-quantitative method, there are 4 categories like hydrocarbon processing equipment, consequence severity, hazard likelihood, and occupancy. Under the 4 category, again, you have the different parameters. If you have the hydrocarbon process equipment, what type of hydrocarbon gas, is the gas or liquid is handled or type of process equipment and process conditions. So these are the parameters is normally taken into account while evaluating the hazard of particular plant. Coming back to the consequence severity, the same as what is the, do you have the congestion is important factor. So identify the confinement and congestion in the process area. So these are the various parameters normally we will be taking into account to determine the performance requirement for any FGS in semi-quantitative method. Once you identify this, all those factors is assigned with some numbers, okay? And based on the numbers, you will be arriving that what is the hazard rank for the particular equipment. So that hazard rank will be, this is the hazard rank, and the hazard rank will be converted into grades. Say for particular equipment, you are coming with the hazard of from maybe 5 to 7, say 6. So that particular equipment will be classified as a grade A. That means typically a high risk equipment. And that high risk equipment must require the detection coverage close to 90%. The probability is mentioned is 0.9. In percentage, it is 90%. If it is a grade B equipment, the detector coverage percentage is 80%. So again, I will come back about what is the 90% and 80%. Now, just to remember that if you have the high risk equipment, the detector coverage required is 90%, medium risk is 80%, and low risk is 60%. Again, these values is coming from ISA standard. It is not proposed from our side. Now, based on that information, as I told, like the initial concept design, the baseline fire and gas mapping layout, based on your experience and you can share, you can look that concept design of the fire and gas system based on the PHA and experience. Once you have done the hazard assessment and then detector requirement specification, now you have to go for third step, verification. Whether the detector provided in your plant based on the hazard is over-specified or under-specified, so that will be verified in the detector coverage verification. So in the detector coverage verification, we have the 2 methods. There are, maybe I will not be talking about theory, so I will tell you the only detector coverage. One is geographic approach method, the second one is scenario-based approach. So there are 2 methods available in the verification. In the geographic and scenario-based, we will be talking now about the geographic approach. So what do you mean by geographic coverage? The geographic coverage is like fraction of that monetary volume, that hazardous, say assume that this is your hazardous volume. Assume that this is 30-meter length and maybe 10 meter or 15 meter breadth and then height is 10 meter. So your volume is like 30 into 10 by 10, something like that. This is your hazardous volume. So what fraction of this hazardous volume being covered by the detectors considered in the plant? So that fraction need to be calculated. If the fraction is 80%, then we have to see that what is the hazard of this plant. If the hazard is categorized as a grade B, that is required 80%, then it meets the target. Say for example, detector provides only 70%, then it is defined as a grade B, that is 80% requirement. Then there is a lack of detectors. So you have to specify or add the detectors to meet the coverage of 80%. So basically it's a geographic coverage of detectors, and then whether that meets the performance requirement as we specified. So that is the geographic approach. Now, the important factor in the geographic approach is like determining the gas cloud size that will be considered for mapping study. Now I'm talking about that gas cloud size design basis. Gas cloud size normally we can be determined by magnitude of the releases, or maybe magnitude of the release means consider that you want to detect some leak from the 25 mm leak or maybe 12 mm leak. So that is your magnitude of the releases. The second approach is you want to detect the volume of the gas cloud. There are two approaches available. Either you specify the magnitude of the release or detect a specified volume of the gas. Okay? So in order to determine the magnitude of the release, maybe I'll just add, So magnitude of the release will have various leak sizes. If it is a very high risk equipment, probably you can look for considered 5 mm gas leak, and then release from the 5 mm gas leak need to be detected. Okay, or maybe you can specify 12 mm leak or 25 mm leak. So this leak need to be detected by the detectors. The gas accumulation, hazardous gas accumulation is, if it is a high congested, high risk area, then you consider the gas cloud size as 5 meter in spherical diameter. And if it is a low congestion or maybe low risk area, you can consider 10 meter gas cloud. Okay. So this is the two bases available for the gas cloud size determination. Now, assume that this is the area of concern. We did a small case study here. Say you are assuming that you want to detect release from the process equipment. Then you can utilize the past software and consider that 25 mm leak or 12 mm leak based on your design basis, and calculate what is the equivalent dia of that particular gas cloud. Okay, so this is the sum of the output taken from the past software. This is the one approach, and you have directly arrived the gas cloud size. So that gas cloud size will be utilized for mapping study. So just remember, this is the one gas cloud size approach. Now the second approach is, this is defined in the UK HSE standard, that you need to determine the gas cloud size before it is bigger enough that it will not produce the damaging overpressure. That means it does not talk about that magnitude of the leak or release. However, it talks about that accumulation of the gas cloud in a hazardous area. If the gas cloud is accumulated and if it catches a fire, that gas cloud produces overpressure more than 150 millibar or 0.15 bar, then that is considered as like considerable explosion, which will lead to further escalation in the plant. So you need to determine the gas cloud before it is bigger enough that it will produce damaging overpressure. So this is as per UK HSE as well as ISA standard. So for that, you need to simulate so many CFD explosions. For gas cloud determination, always it is recommended to go for CFD tool. So you had to simulate so many CFD explosions at the various locations. This is a typical example or pictures. Say this is a gas module, any gas leak, you have the gas accumulation like that, and you can do the explosion analysis in the CFD and check that what is the overpressure you are achieved. If the overpressure is less than 150 millibar, then that is your gas cloud size, target gas cloud size. If the overpressure is higher than 150 millibar, then you have to further reduce your gas cloud size and do the explosion analysis. So like that, you have to do as a trial and error method. I did one case study using KFX software, is a CFD tool, DNV KFX software. Like first initially I had taken the methane as a hazardous material handled in the module, and I had taken the gas cloud, not 5 meter cube, it is a 5 meter dia, okay? So I had taken the 5 meter dia gas cloud size in a congested module, and based on the explosion analysis, it is 5 meter dia gas cloud is not producing the overpressure of 150 millibar. It is lower than the 150 millibar. So now I have increased the gas cloud size to 10 meter dia. Once you, you can just click this video. So you can see that the gas cloud size explosion in the KFX software, when you take 10 meter dia, it is producing the 0.1 bar. So still it is not touching the 150 millibar. So, but still recommended that it's a normal practice. The gas cloud size should not be more than 10. But I have seen some people taken 15 meter and 20 meter also. But still, without proper justification, it's better to go with the conservative approach 10 meter. Okay. So here you can take the 10 meter. You can take as a target gas cloud size for mapping study. Now, the similar approach I had taken for the hydrogen because I want to compare with the different material for the same geometry structure, how the gas cloud size varies. And this 5 meter equivalent dia of hydrogen, for the hydrogen, you can see that it is still not producing 150 millibar. It is maybe max you are reaching that 0.025 millibar. Sorry, 0.025 bar. So it is a 2.5 millibar. Now, similarly, I had taken the hydrogen with a 10 meter gas cloud size. Now, from the 10 meter gas cloud size, I am getting the overpressure of more than 0.3 bar, that is more than 300 millibar. So, for the same geometry structure, if the hydrogen is handled, the overpressure generated is so significant that you cannot use the 10 meter as a target gas cloud size. That is the reason normally as a consultant we propose to take 5 meter, but again I will tell you that what is the disadvantage of again taking 5 meter for the analysis. So since it is falling under 5 to 10, I try to do in a different way. Like I had taken one more example of 8 meter dia. For 8 meter dia also still I am getting 200 millibar, close to 200 millibar. Still it is higher than 150 millibar. So now I had done with the 7 meter dia. So 7 meter dia is producing close to 150 millibar, but lower than 150 millibar. So accordingly, I have decided that for the current module, if the hydrogen is handled, probably 7 meter gas cloud size is effective or efficient, and it's optimum gas cloud size that can be utilized for the mapping study. So just to have some summary of all the CFD explosion analysis, if the methane of 5 meter gas cloud size, the maximum overpressure produced is close to 0.18 millibar. If the same methane of 10 meter gas cloud size, it was producing close to 100 millibar. So, and whereas in the hydrogen case, the 10 and 8 was producing higher than the target overpressure, that is more than 150 millibar, whereas 5 and 7, it is okay, it is less than 150 millibar. So now you can decide that what is the target gas cloud size we can consider for the mapping study. And once you determine the gas cloud size, next important step is locate the detectors and then in an optimum way and then check that whether the detector is covering the entire volumetric area. So this is the methane I had taken. This is the Detect 3D software is used where the detectors with the different locations to cover the entire module we have modeled, and finally we have achieved that 81% of geographic volume is covered with the 9 number of detectors. Okay. So if the same module is operating with the methane, with the 10 meter gas cloud size and 9 number of detectors is achieving the 81% coverage, it achieves the target. Assume that this is the grade B process module. Similarly, if I'm taking hydrogen, because typically hydrogen we used to say that take 5 meter as a gas cloud size. When you take the 5 meter as a gas cloud size, you can see small gas clouds, okay? But actually this is not the gas cloud. This is the that detector field of influence, but the main intention is the gas cloud should not be bigger enough than this so that we'll have a serious explosion. So it is the indirect way of representing the gas cloud. And number of detectors for the same module, if you have hydrogen with a 5 meter gas cloud dia, is 42 numbers. Just imagine that earlier for methane, you are supposed to achieve the coverage with the 9 number of detectors, whereas for the hydrogen, you require 42 number of detectors. Now you can assume that how much of detector quantity is increased to achieve the performance reduce the risk. So since in the similar way I had done, since we have executed that CFD explosion and determined that gas cloud size, okay, so we arrived at 7 meter is the gas cloud size for the particular module, considering all the obstructions, okay. Now what is the number of, now the same thing is implemented in the Detect 3D software. Now we arrived that 21 number of detectors is sufficient to achieve the coverage of 83% or maybe 80%, and this meets the requirement. So there is a reduction of 50% detectors. If you say, like, if you are assuming that it is a hydrogen facility, take 5 meter is a gas cloud, 5 meter is a gas cloud, and then once then you are arriving the 42 numbers, and doing the explosion analysis, determining the exact gas cloud size, okay, by the CFD explosion will be the effective way in order to reduce the detectors. Also, that meets our requirement. So there is a 50% reduction in the detector quantity once you do the CFD explosion and determine the coverage. So that is about the gas cloud, flammable gas cloud mapping study. Now coming back to the fire. Okay, the fire detectors is purely works on the principle that any fire of 1 foot by 1 foot hydrocarbon fire that need to be detected by the detectors. So it is like raycasting mechanism is utilized, like how much of geographic volume will be seen by the detectors. So that it is, you can see like that. So this is the detectors located in all the 4 corners. How much of volume will be seen by the detectors. So this region, you can say some obstructions and detector not able to detect, and accordingly there is a volume or vacuum in that area. So like that, all the detectors we have provided in this area, and how much of volume will be seen by the detector is determined, and that volumetric fraction is achieved or not, that will be checked. Probably I have not done kind of verification for the flame, because flame detector is kind of straightforward. This is a contour representation for the flame detector. And now we are coming to the next scenario based. As I told, like we have the geographic based mapping study that is based on the determining the gas cloud size, and that is implemented in the CFD tool. Now scenario based approach coverage. So scenario-based approach is like, it is defined as how many scenarios, how many number of scenarios will be detected by the detector. So in a process module, assume that you have the 100 number of scenarios. So how many number of, among the 100 number of scenarios, how many of them will be detected by the detectors? So that divided by total, that should meet your target. Say for example, you are providing some X number of detectors, and you are achieving the 80 number of scenarios will be detected by the detector, then 80 divided by 100 is your percentage coverage for the particular module if you are following the scenario based approach. So it talks about that hazard scenarios from the process equipment within a defined and monitored process area that can be detected considering the frequency and magnitude of the hazard scenario. In scenario coverage, frequency for each scenario is determined, and each piece of equipment has a model for consequence created using Gaussian or computational fluid dynamics. So one of the big effort required in the scenario based is like each and every scenario need to be modeled using CFD tool. So if you are identifying some 100 number of scenarios, then 100 number of scenarios must be modeled. Then only you can able to see that the physical behavior of the gas cloud and where the high probable spot for the gas detectors. So basically we will be identifying the high probable spot in a process module where you will have more probability that gas will be there, and then detector will be detected by the detectors. So in the source time modeling, it's a similar, as I told, it's already similar approach to the QRA. You have to identify all the sections using piping and instrumentation diagram, and develop the process conditions and composition, operating pressure and temperature, and all those scenarios need to be And also you have to calculate the frequency. The failure frequency is same as the quantitative risk assessment, like identify all the equipments, all the flange connections, all the walls, all the ESD systems, compressors. So you have to identify all the items in a process piping and instrumentation diagram, and that need to be taken, that statistical frequency data will be taken from the IOGP. That will be utilized for the frequency analysis. Once you do that, then this is assume that this is a small module. This dots indicates that potential leak sources. So you have to identify all the potential leak sources. In a equipment, so potential leak sources is like equipment itself, along with you have so many flange joints, like incoming flange, bottom outlet flange joints, vapor outlet joints, and also so many instrument tappings. So you have to identify all those potential leak sources in the 3D model. So that is another important aspect, because these all potential leak sources is one hazard scenario in the scenario-based approach. So in a small module, you assume that you identify some 100 number of potential leak sources, then you need to model 100 number of such release scenarios in the CFD to understand the physical behavior or pattern of the gas cloud based on the actual wind pattern and the wind direction. And so you have to develop or model all those things in the gas dispersion modeling. Basically, either you can use FLAX software or KFX software for dispersion analysis. And this is the typical gas cloud by considering all the obstructions in a geometry, in a process plant. Once you model all such scenarios, you will be plotting the risk like that. Assume that the first risk contour or risk plot is without detectors. Assume that there is no detector. So without detectors, this is the risk picture. And this red color is -3 risk, this orange is -4, yellow is -5, and this is -6 risk contour. Okay? Now you can see that you can spot it out that which is high risk equipment, and then where we need to identify the detectors. Okay? Now by seeing this, you know that this is a high risk area, and then provide the install the detectors at strategic locations, and assume that you are installing detector here and here, and then re-verify that whether the detector, what is the risk after considering the detectors. That means if you provide detector here, any scenario coming from this equipment most probably will be contacted by this detector, and it will detect the leak or that scenario. Therefore, once you plot after detectors, this will look like that. This is a mitigated risk. Mitigated means including the fire and gas detection, the risk is reduced. So because you are installed the detector, those scenarios will be detected by the detectors. So you have the less risk zone. That means it's a mitigated risk plot. So basically, but as I told that in the risk assessment, there is no zero risk kind of thing. Always you have the risk. So this is a kind of residual risk. Further risk reduction is not going to give much benefit. So that is the understanding. So still, but it is a less risk, it is an acceptable range or tolerable. Therefore, we can live with that. So this is the kind of assessment we normally perform in the scenario based. Okay, I think with that I can close my presentation. Thank you. If you have any questions.
네, 혹시 괜찮으시면은 저희 Q&A 세션 진행하기 전에 제가 한글로 간단하게 조금만 정리를 하려고 해요. 네, 이미 발표를 많이 해주셔가지고 조금 지연될 수도 있을 것 같은데 간단하게만 몇 가지 슬라이드만 말씀드리겠습니다. 먼저 처음에 이제 말씀하셨던 게 파이어 앤 가스 시스템의 리스크 컨셉션 자체가 직접적으로 리스크를 감소시키는 것은 아니지만 에스컬레이션을 막기 위한 것이라서 그런 미티게이션이나 아니면 에머전시 리스폰스가 제때 이루어질 수 있도록 더 큰 피해가 이루어지지 않도록 막는 것이라고 말씀을 하셨고, 또 그 다음에 잠시만요. 네, 지금 여기 나와 있는 이 프로세스들은 FNG 매핑이 FGS 시스템 디자인 프로세스인데, 이건 ISA TR840007이라는 국제적인 가이드라인에 나와 있는 내용이고요. 처음에 파이어 앤 가스 하자드를 어세스먼트를 먼저 하고, 그 다음에 어떤 스페시피케이션을 적용을 할 것인지 그리고 그 스페시피케이션에 대해서 우리가 가지고 있는 디텍터들은 어느 정도의 퍼포먼스를 내는지 베리피케이션을 하고 그 이후에 미티게이티드 된 완화된 리스크를 확인한다고 생각을 하시면 될 것 같습니다. 그래서 어떤 방식으로 이루어지는지 스텝들이 여기 슬라이드에 나와 있었는데요. 먼저 처음에 어떤 부분을 분석을 할지 대상을 지정을 하고 그 다음에 그 대상에 대해서 어떤 사항들이 고려가 될지, 뭐 얼마나 컨제스티드 되어 있는지, 아니면은 어떤 물질이 사용되었는지 등을 분석을 합니다. 그 다음으로는 결과를 분석을 하는데요. 이 결과를 분석하는 방식으로는 CFD를 이용해서 조금 더 정확하게 이 가스가 어떻게 분산이 되는지 모델링을 하는 방법이 있고, 또는 파스트를 통해서 어느 정도까지 분산이 되는지 방법이 있습니다. 두 방법의 차이점이라고 하면은 파스트 같은 경우는 직접적으로 지형 모델링이 들어가지는 않잖아요. 하지만 CFD 같은 경우는 직접적으로 저희가 그 Geographic 모델링을 받아서 인풋하고 계산이 되기 때문에 그런 설비들이 맡고 있는 부분들이 고려된다는 차이점이 있다고 보시면 될 것 같습니다. 네, 다음으로는 빈도를 분석하고 완화되지 않은 결과를 관찰을 합니다. 여기서 만약에 현재 존재하는 뭐 감지기들로 충분하다 하면은 뭐 더 이상 스터디를 진행하지 않으셔도 괜찮으시겠지만, 혹시 우리가 목표한 것보다 현재 결과가 조금 불충분한 것 같다, 그럼 그럴 때에는 Fire Gas Mapping 스터디를 적용하시는 걸 고려해 보실 수 있을 것 같습니다. 네, 퍼포먼스 타겟 같은 경우는 감지기로, 그래서 우리가 감지기로 어느 정도까지 리스크를 줄이는 것을 목표로 하는가라고 생각을 하시면 될 것 같고요. 네, 잠시만요. 네, 저희는 주로 반정량적인 방법을 채택을 하고 있는데, 이 네 가지는 그 반정량적인 방법에서 어떤 사항들이 고려되는지라고 생각을 하시면 될 것 같습니다. 네, 이 네 가지 사항을 고려해서 저희가 이제 실제로 스터디를 진행을 하게 되면은 어쌔션 레지스터를 공유를 해드리는데, 거기에 각각의 항목들이 뭐 몇 점의 점수를, 뭐 예를 들어서 고합이면은 더 높은 점수를 부여하고 저합이면은 더 낮은 점수를 부여해서 그 점수의 총합으로 이런 하자드 랭킹을 매기고요. 그걸 그레이드로 변환해서 디텍션의 커버리지를 매깁니다. 점수가 높을수록 더 위험하니까 더 많은 범위가 커버될 수 있도록 보통 목표를 설정하고 있습니다. 그리고 이 이후에 이제 베이스 설계를 진행을 해주시면은 그 진행해 주신 설계가 어느 정도로 커버리지를 하고 있는지 확인을 하고, 그것이 이제 저희가 이 앞에서 설정한 타겟에 모자랄 경우에는 뭐 위치라던가 대수 등을 조정해서 옵티마이징을 진행을 하고 있습니다. 이 커버리지를 확인하는 방법으로는 Geographic 어프로치가 있고 시나리오 베이스드 어프로치가 있는데요. 시나리오 베이스드 어프로치는 조금 더 맨데이도 많이 들어가고 복잡한 과정이라서 저희는 주로 지금은 Geographic 어프로치를 많이 사용을 하고 있고요. 간단하게 조금 더 설명을 드리겠습니다. 네. Geographic 어프로치는 여기 딱 보시면은 네모를 설정해서 그 안에 뭔가 차지하고 있는 느낌이잖아요. 그래서 공장 내 부피를 기준으로 실제로 감지기가 커버하고 있는 영역이 몇 %인지 그 비율을 측정하는 방법으로 생각을 하시면 될 것 같습니다. 여기서 중요한 게 이 각각의 감지기들이 감지하는 범위를 얼만큼으로 설정할 것인지, 그걸 결정하는 게 가스 클라우드 사이즈인데, 이 가스 클라우드 사이즈를 어떻게 설정하는지에 대해서 설명을 좀 자세히 해주셨습니다. 두 가지 방법이 크게 있는데요. 먼저 노출의 규모를 결정해서 어느 정도 컨제스트 되었는지 등을 고려해서 파스트 등으로 계산하는 방법, 또는 데미지의 기준을 설정해서 각 데미지에 도달하려면 어느 정도 노출이 어느 정도 노출이 됐을 때 각 데미지에 도달하는지를 계산해서 측정하는 방법이 있었습니다. 전자 같은 경우는 이렇게 파스트로 계산하는 것을 보여주셨고요. 후자 같은 경우는 아까 전에 각 직경별로 설정을 하셔서 이렇게 기준을 넘는지 안 넘는지를 관찰을 해서 이 기준보다 넘으면은 그건 좀 위험한 것 같다, 그런 식으로. 그래서 너무 이 직경을 너무 크게 잡으면은 사실 감지기가 덜 필요할 수는 있지만 조금 더 위험하겠죠. 그리고 너무 작게 잡으면은 훨씬 더 안전하겠지만 너무 감지기가 불필요하게 많이 필요할 수 있기 때문에 이 두 가지 사이에서 최적의 지점을 찾는 것이 조금 더 효율적인 방법이라고 생각하시면 될 것 같습니다. 네, 시나리오 베이스 같은 경우는 그리고 플레임 디텍터 같은 경우도 비슷한 방식으로 진행이 돼서요. 여기 보시면은 이 각 설비들이 가리고 있는 부분을 제외하고 남은 보이는 부분만 고려를 해서 몇 %의 비율이 감지가 되고 있는지를 평가를 합니다. 시나리오 베이스 같은 경우도 이건 짧게만 좀 말씀을 드리려고 하는데요. 시나리오를 설정을 해서 각 시나리오를 모두 CFD로 계산을 하고 그 전체 시나리오 중에서 몇 개 시나리오를 우리가 감지할 수 있는지를 타깃으로 설정을 합니다. 그래서 이런 경우는 QRA와 유사하게 각각 모델링을 해서 결과를 넣는 방식이라고 생각을 하시면 될 것 같습니다. 혹시